Hi, good morning. Assalamualaikum. We meet again in CHM 477. This is my lecture number 10 for this subject of inorganic chemistry. And for lecture 10, I'm going to be talking about coordination chemistry. Now, coordination chemistry is the field of inorganic chemistry that deals with transition metal complexes. Yeah. So there is a history to coordination chemistry. Yeah, like as everybody knows from hundreds of years ago, that the main driving force for any chemical reaction to occur is to achieve stability. Agree? Because something will become more stable when they react. So they react. If through the reaction stability is not increased, then that reaction is not going to happen. So chemical reaction, the driving force for them are to achieve stability. This has been well established by the chemical rule of thumb, which is the octet rule or the rule of 8. Yeah? Atoms of one element tend to combine with atoms of another element in such a way that each atom has 8 electrons in the outermost shell, just like that of the noble gas. Now, this is what is known for chemists for many, many hundred years ago. This rule of 8 is then extended to become the 18 electron rule or the effective atomic number rule to account for the d orbitals, because we all know that d orbitals, there are 5 of them, and 5 d orbitals can accommodate up to 10 electrons. So if you start getting s, p, and d in one shell, so to complete the valence or to fully fill all the orbitals, you need 18 electrons. So going on to the third series or third layer of the periodic table, we start applying the 18 electron rule instead of the octet rule. The octet rule is true only for the first and second shell. The third shell, you start getting the 18 electron rule because of the existence of the d orbitals in the third shell. Now, what has been puzzling a lot of chemists many hundred years ago is that some compounds that looks to be stable, yeah, seemingly stable compounds, when a compound is stable, usually it will not undergo any chemical reaction because it is already stable. But however, chemists have observed that these stable compounds still can react with another stable compound. And this reaction produces another stable compound. And this has been perplexing chemists for many years. There has been a puzzle to a lot of chemists for many years. So in the 1890s, this is year 2020. So more than 200 years ago, or about 200 years ago, a Swiss chemist by the name of Alfred Werner, who was born in 1966 and died in 1919, Werner carried out a series of experiments on cobalt 3 chloride. He had cobalt 3 chloride salt and he had ammonia. Both compounds are stable. So he did not expect to see any chemical reaction happening when he added cobalt 2 chloride into ammonia. What he expected would be just a solution. Dissolving cobalt 2 chloride into ammonia, he expects to have a solution of cobalt 3 chloride in ammonia. However, what he could not understand is when he added cobalt 3 chloride into ammonia, he was puzzled by the fact that this form stable compound that has a different formula. When he added cobalt 3 chloride, which is a solid, into ammonia, which is liquid, what he obtained is another solid. He obtained a different solid with the formula of COCl3 with 6 ammonia. So he was very, very puzzled. And he said, how come the cobalt 3 chloride, which is stable, reacts with ammonia, which is stable, and giving me a stable complex, a different stable compound with the formula of COCl3 6NH3. So that he couldn't understand. So even though he could not understand that, he still carried out his experiments. He has a very curious mind, and he allows his curiosity to lead him to great discovery. So he then take this solution, this copper chloride 6, COCl3 6NH3. He added silver nitrate solution to the product, and he observed that some of the chloride ions precipitate as silver chloride. Now, we all know, as elementary chemists, we all know, we have learned chemistry so many years, we all know that to identify chloride, you add silver nitrate, and you're going to get silver chloride, which is a solid. So if the chloride is free to react with silver, then it is going to produce a white solid of silver chloride. So, to his surprise, this product, COCl3 6NH3, when he added silver nitrate to it, he managed to get silver chloride white precipitate. And he also observed something more puzzling. He observed that the amount of silver chloride that was formed was related to the number of ammonia molecule which is bound to the cobalt chloride. So when he had cobalt Cl3 6NH3, he added silver nitrate, he get 3 equivalent amounts of silver chloride. But when he reduced it, the ammonia reduced it to 5 ammonia, he only got 2 equivalent amounts of silver chloride, not 3. And then when he further reduced the amount of ammonia attached to this COCl3, he only get 1 equivalent amount of silver chloride. And when he further reduced the amount of ammonia in this compound, he didn't get any silver chloride. So he was extremely puzzled. So he was thinking this over, and then he came up with what is now known as the Werner's theory of coordination compounds. Yeah, the Werner's theory of coordination compound. So Werner, well, his name was Alfred Werner, in 1898, which is about 20 years before he passed away, he came up with a hypothesis. How old was he in 1898? He was born in 1866. So he was 32 years old when Werner came up with his hypothesis. So his hypothesis, to explain this observation that he saw, he said, okay, the central metal atom in coordination exhibits 2 types of linkages. The first one he called the primary valence. The second one he called the secondary valence. Now, in modern chemistry, the primary valence is oxidation state, oxidation number, and the secondary valence is coordination number. But he didn't know that at that time. I'll explain it to you later. Now, the primary valence are generally ionic in nature, referring to the interaction of the metal with anions where the charges are balanced out. So this is the oxidation state, just like your sodium chloride, Na plus. So the primary valence of sodium is 1. Huh? The secondary valence are non-ionic. The first one is ionic in nature. The second one is non-ionic. And these secondary valences are generally satisfied by negative ions or neutral molecules. The secondary valence is fixed for any given metal and it is equal to the coordination number. So the secondary valence is the coordination number, whereas the primary valence is the oxidation number. Now, the ions bonded by secondary valences to the metal center exhibit characteristic spatial arrangements corresponding to different coordination numbers of the metal. Such spatial arrangements are now known as the coordination polyhedral or coordination number, where the species within the square brackets are called complexes or coordination entities, and the ions outside of the square brackets are known as the counter ions. So this may not be making a lot of sense to you now, but as we go along, it will be perfectly clear. So this is what Werner discovered. So COCl3 6H2O in modern coordination chemistry is written as CO ammonia 6 in the square bracket, and the Cl3 is outside of the square bracket. So this one in the square bracket is called the complex ion, and the chloride on the outside is called the counter ions. Okay, let me write that down. Pause it. The one in green, or the one written in green saying complex ion, is this part of the compound which is located in the square bracket, and the Cl3 located outside of the square bracket is called the counter ions. So in here, cobalt has bonded to 6 ammonia, making a complex ion having a charge of +3. Because ammonia doesn't have any charge, cobalt is cobalt 3. So this whole thing in the square bracket has a charge of +3, and those charges are being balanced out by the 3 chloride. That is why when Werner reacted this compound, which actually is this compound, when he reacted it with silver nitrate, the silver will pick up this 3 chloride. Whereas in here, you have COCl3 5NH3. The cobalt, remember cobalt has coordination number of 6. Here it says the coordination number. Okay. And this coordination number is almost fixed to 6 for cobalt. Yeah. So cobalt has here 6 ammonia, in here 5 plus 1, 6, in here 4 plus 2, which is also 6, in here 3 plus 3, which is also 6. So whatever is remaining will become counter ions, and the chloride that became the counter ion will be picked up by the silver nitrate to make silver chloride. That is why you have these observations that he saw. So he used the primary valence, which is the oxidation number, and secondary valence, which is the coordination number, to explain his observation. Oh, let me put okay. Now, in modern terms, the compound cobalt Cl3 6NH3 is said to possess a cobalt center with the oxidation state of +3 and coordination number of 6. Yep. Coordination number of 6. Let me put that there. Yeah. IE. Yep. So the coordination number is how many ligands or how many entities does the metal compound bond to. In this case, 6. So coordination number, valence, secondary valence of 6. And the primary valence is 3, which is the oxidation number. Yeah. The Werner's theory of coordination compound is an attack of the then current, firmly entrenched valence theory founded by the supreme patriarch of structural organic chemistry, Auguste Kekule. Kekule had a different when he was a very notable chemist at that time, and it was not going the same way as what Kekule was describing. So what Werner was describing was something that challenges the current understanding, chemistry understanding. However, many renowned chemists recognize Werner's theory, this theory that he postulated. Here, they recognize Werner's theory as being revolutionary and excellent scientific achievement, and it is appreciated in wider chemical circles. So Werner is the father of coordination chemistry. So you're learning about coordination chemistry. Now you know about Werner. Werner is the father, the founding father of coordination chemistry, with his very, very sharp observation and hypothesis. Okay. So some chemist who is Werner's ex-supervisor when he was doing his PhD, which is Arthur Rudolf Hans, he said what Werner postulated was an achievement which stands far above the ordinary and which represents a significant advance in the field of theoretical chemistry, although for the present it consists only of elimination of incorrect and damaging views on valence and the so-called valence unit. So with this paper, the author has proven, or Werner has proven himself to possess extraordinary originality and has also very fortunately overcome the difficulty of presenting his ideas clearly and comprehensively. So this is the comment of his ex-supervisor upon his Werner's hypothesis. So in 1913, Werner, with his finding, became the first inorganic chemist to win the Nobel Prize and the only one before 1973. So there is a 60-year gap between Werner and somebody else in inorganic chemist to win Nobel Prize. Nobel Prize is uh, awarded to people whose finding in science changed the human life for better. Yeah. Anybody, any scientist that made a discovery and his discovery changes human life for the better is eligible to be nominated for being a Nobel Prize winner. So Werner's contribution to human life betterment is actually very, very big because he actually won the Nobel Prize. Yeah. He won the Nobel Prize in Chemistry for proposing the octahedral configuration of transition metal complexes. Octahedral means here you have the cobalt attached to 6 ammonia and making an octahedral arrangement. Octahedral is 1 cobalt in the middle and 1 ammonia at the top, 1 ammonia at the bottom, and then 4 ammonia to the 4 corner of the ASIL. So his suggestion of octahedral configuration for transition metal complexes gave him the Nobel Prize because the scientists, the committee that evaluated his work really understood the importance of his finding. But amazing as it was, Werner's theory could still not be able to explain the color, the magnetic, and the optical properties of coordination compounds. It is able to explain the chemical properties, the why the cobalt is making a bond with ammonia despite already being stable. That can be explained by Werner's theory. But Werner's theory still could not explain why the compounds are colored, why they have magnetism, and why they have optical properties. So that leads that leads the chemistry to develop to become the modern coordination chemistry. So, and you're going to meet this later when we talk about crystal field theory. Before we go into crystal field theory, I'm going to introduce you to coordination compounds. Yeah? Coordination compounds are generally made up of a central atom, usually a metal, surrounded by a cluster of ions or molecules called a ligand. You have a metal in the middle, and you have ligands, or ligands are either ions or molecules that are attached to that central metal. So we call that ligand. Yeah. Two types of coordination compounds can be formed as a result of combination of central metal and ligands, namely molecular coordination compounds or ionic coordination compounds. If this is not making sense to you now, just stay put. You are going to see this clearly later. If the cluster of metal and ligand is uncharged species, they're called molecular coordination compounds. And if they do have a charge, either positive or negative, they're called ions. The charge of this complex ion has to be balanced by a counter ion of the opposite charge, either another complex ion or a simple ion. The complex ion and its counter ion form an ionic coordination compound. So this is what is meant by Werner's theory. This is a representative of square bracket. It should actually be going all the way down, making a bracket there, and all the way down, making a bracket here. Let me show that in drawing. Okay, this like a figure 7 here that you have in your notes is actually a symbol of this complete square bracket, yeah? So if you see a partially formed square bracket with a charge, that actually represents this whole square bracket on the left and the right. So if I delete that, if I delete this and I delete that, it can be represented by this half-formed square bracket with a charge. Yeah. Now, that makes you understand that this whole thing, this cobalt center and 6 ammonia, there is 1 ammonia, 2, 3, 4, and 5, and 6 ammonia. These are all called the complex ion. These are called the complex ion, and cobalt hasn't got ammonia doesn't have any charge. Cobalt is initially cobalt 3 because he reacted cobalt chloride, and cobalt chloride is COCl3, and the cobalt is 3 plus. So the charge of the cobalt is carried through outside into the complex ion, and this whole complex ion has a charge of plus 3. Now, the charge of plus 3 will be then neutralized or will be countered by the 3 chloride. 1, 2, and 3 chlorides. So this is called the complex ion, the one that's in the middle. This one here that I'm making a circle of. That's your complex ion. And the green, which is this one, the 2, and the 3, those are called counter ions. So this is what is explained here. the charge of this complex ion, which in the case of what we saw down there was 3 plus, has to be balanced by a counter ion of the opposite charge, which is in the case of picture here, which is chloride. It can be a simple ion like chloride. It can be also another complex ion, as long as it has an opposite sign charge. Yeah. So this combination of complex ion and its counter ion form ionic coordination compound. So this is ionic coordination compound. You can also have molecular coordination compound, but that's going to be discussed later. Yeah. So this is the picture and the representation of it is here. Yeah. This is the representation of the picture up there. This is cobalt 6 ammonia 3 chloride. This is cobalt 6 ammonia and with a plus 3 charge and 3 chlorides. Now I'm going to explain to you why you have an arrow pointing from the nitrogen of the ammonia into the cobalt for each case. That I'm going to explain to you much later due to when we discuss about ligands. Yeah, here it is. This is the ligands. The plus 3 charge, now let me explain this diagram first. The plus 3 charge of the complex ion in the square bracket is balanced with 3 chloride counter ions. Therefore, the primary valence, which is the oxidation number, is 3. And the secondary valence, which is the coordination number, is 6. So cobalt is coordinated to 6, so the coordination number of cobalt is 6. But cobalt has oxidation state of 3 plus, so it has a primary valence of 3. Right. Bear with me. This is not too difficult. You just have to follow my lecture carefully. Now, I did mention the word ligands just now. Now, what are ligands? Ligands can be neutral molecules. They can also be ions. Now, they have to possess at least one lone pair of electrons that can be donated to a metal center to form a dative covalent bond, which are also called coordinate bond. Yeah. For a molecule or for an ion to become a ligand, it has to have one lone pair of electrons. Lone pair of electrons means electrons that are not bonded, a pair of electrons that are not bonded to a metal, just like you see in ammonia. Can you recall ammonia? Ammonia is N with the 2 dots at the top and then 3 bonds to hydrogen. So the 2 dots at the top is the lone pair of electrons, and ammonia, because it possesses that lone pair of electrons, ammonia is a ligand. Because that lone pair of electrons can be donated to a metal center, given to a metal center to make a bond. Yeah. So that lone pair of electrons donated to a metal center, for example, a cobalt, makes a bond because the lone pair of electrons are being shared. When you have shared electrons, you have a covalent bond. But this is not any ordinary covalent bond. This is called the dative covalent bond. Ordinary covalent bond is when you have, for example, hydrogen bonding to oxygen. One electron from hydrogen, another electron coming from oxygen. So there are 2 electrons making a pair, and the 2 electrons are shared between the hydrogen and the oxygen. That's called an ordinary covalent bond. But in the case of dative covalent bond, both the electrons come from the one source. In the case of ammonia, the lone pair that is being shared with the metal comes from ammonia. So that is called a dative. Dative means that the lone pair of electrons being shared by the ligand and the metal come from the one source, which is the ligand only. Yeah, dative. Sometimes they are also called coordinate covalent bonds. Yeah. So ligand donates its electron to metal. Electron donors are called Lewis base. Anything that donates electrons is called a base. Anything that accepts electron is called a Lewis acid. So ammonia is a Lewis base and metal is a Lewis acid. And the interaction between the ligand and the metal is called a Lewis acid-base interaction. And that is actually what makes coordination compounds. Lewis acid-base interaction where metal is the Lewis acid, which is the electron acceptor, and ligand is the Lewis base, which is an electron donor. Now, can you tell me another molecule that can become a ligand that you have encountered before when we are learning VSEPR? Well, we have ammonia. Another? Can you recall? Water. Yes, water has two lone pairs of electrons. Yeah, you have oxygen with two lone pairs of electrons and two bonded pairs with hydrogen. So water can also make a good ligand because it has lone pair of electrons. Chloride. Chloride also has lone pair of electrons. Yeah. Now, atoms in the ligand that are directly bonded to the metal is called the donor atom. Like you have ammonia, the nitrogen, this nitrogen has lone pair of electrons. So it is the donor atom. Hydrogen is not the donor atom. Nitrogen is the donor atom. Yeah. For example, the donor atom in the complex ion CONH63 plus is nitrogen. Now, depending on the number of donor atoms, ligand can be classified as monodentate. Okay, I'll leave this for a while, but I want to concentrate on this picture. So, the arrow means that the shared electrons come from one source, which is in this case nitrogen. So that is why in this diagram you have arrow coming from nitrogen to cobalt. Sometimes student will make a mistake of drawing NH3 like this. NH3 like this when the nitrogen is closest to the cobalt is correct. But if it's on the other side of the cobalt like this, it will become H3N. Why do we write it as H3N? Because we would like this nitrogen to be closest to cobalt because it is nitrogen which is the donor. It is not hydrogen. So if you draw N here, H3 here, that means you have drawn it wrongly. Yeah. N must be directly coordinated to cobalt, even if it means you have to write H3N. Yeah, it's actually NH3. So see how I'm being very careful to draw the nitrogen to be directly donating its lone pair of electrons to cobalt, this nitrogen, not the hydrogen, not the hydrogen. So if you draw let me see whether I can do this, whether I can show it to you. Sometimes students make a mistake like this. Sometimes students make a mistake and they're so used to writing ammonia as NH3, ammonia. So what they do, they just write ammonia and they do this, like that. That is wrong because this particular arrow tells me that the hydrogen is the donor donor atom, which is not correct because hydrogen doesn't possess any lone pair of electrons. It is the nitrogen which is the donor atom, so this has to do that. Yeah, that would be more correct. But 7 is not correct, so I'm going to delete this. I just want to make a point that you have to be careful to draw your arrow from the actual donor atom to the metal center. So I'm taking that away, deleting it. So be careful when you are drawing a coordination compound. Okay. Now, depending on the number of donor atoms, ligands can be classified as monodentate, bidentate, or polydentate. Ammonia and chlorides are ligands that have only one donor atom each, therefore they are called monodentate. Now, dentate means teeth, gigi, yeah? So, one donor can only bite at one point. But if in the molecule you have two donor atoms, it can bite at 2 points. So it has two teeth. Teeth, dua gigi, yeah? So bidentate, if there are two donor atoms. If there are three donor atoms, you say tridentate. If there are too many donor atoms, then you say polydentate, yeah? Polydentate. So ammonia and chloride are ligands that have only one donor atom each, therefore they are called monodentate ligands. Oxalate ion, are you going to meet oxalate ion in your lab maybe this week or next week? Now oxalate ion, which is C2O4 2-, is a bidentate ligand because there are two oxygen atoms in that oxalate that can donate the lone electron pair to the metal center, forming two dative covalent bond. Let me show you this. Okay. So that is oxalate, C2O4. C2O4 is oxalate. It actually comes from oxalic acid, where there is H here and there is H here. So when these two have lost their protons, they become oxalate ion, and the oxalate ion can bind to metal through this oxygen and that oxygen, making it biting the metal at two different places. So oxalate is called a bidentate ligand. The same with ethylene diamine, EN. Ethylene diamine is also a bidentate ligand because it has one and two donor atoms. This nitrogen can donate to metal, that nitrogen can donate to metal, making a bidentate ligand. So these are your bidentate ligand. This is your oxalate. This is your ethylene diamine. But what's listed at the top here, they are all monodentate ligand. Ammonia is one monodentate ligand which doesn't have any charge. So it is a molecule. Chloride has lone pairs of electrons, many of them, 4 pairs of lone electrons. So chloride also is a monodentate ligand, because it can, well, one chloride can only donate once, it cannot donate two. Thiocyanate, this is thiocyanate. This is also a monodentate ligand. It cannot, sulfur and nitrogen both possess lone pair of electrons, but the same thiocyanate cannot donate to the same metal from two different donor atoms. It cannot donate from nitrogen as well as sulfur. It can only donate at nitrogen. Carbon monoxide is like this. It can only donate from carbon. So when you have a choice whether it is sulfur or nitrogen, carbon or oxygen, you have to choose which one is the most likely donor atom. Now, the most likely donor atom is the least electronegative atom. Between oxygen and carbon, oxygen is more electronegative. So it is not likely that oxygen will donate its electron to a metal. It will be the carbon, because carbon is least electronegative or more electropositive. So when you have sulfur and nitrogen like this, which one is least electronegative? We will say sulfur. Sulfur is least electronegative, so it is very likely that sulfur is going to be the donor atom rather than the nitrogen in this case. Yeah, right. And there is also a term of polydentate ligand, many teeth ligand. This is a one-tooth ligand, ligand dengan satu gigi. Here you have a bidentate ligand. Dentate in Greek means, again, from the word dental, dental teeth. So you have bidentate ligands, ethylene diamine and oxalate, but polydentate, many teeth. So polydentate, which is EDTA, ethylene diamine tetraacetate ion, EDTA, it has 1, 2, 3, 4, 5, and 6. It has 6 possible donor atoms that will be able to donate to the same metal center. So 6 teeth ligand called polydentate ligand. I think, yeah, this is one example. This is the example where this nitrogen, this is a polydentate EDTA. EDTA. If you do not recognize this molecule as EDTA, you just have to go back here. Yep. It binds from these two nitrogens. Can you see it here? Maybe I should take it down here. Maybe you will be able to see it properly. Yeah. Oops. Let's make it small. Yeah. Make it smaller. Yeah. So this is the EDTA ligand, ethylene diamine tetraacetate EDTA ligand. So this nitrogen is that. This nitrogen is this. This oxygen is that. And then that oxygen is this. So 1, 2, 3, 4. And 2 more. One oxygen here is this. And another oxygen here is that. So you have 6 donor atoms in EDTA, making EDTA a polydentate ligand. So the number of atoms with which polydentate ligand bind to metal center is called its denticity or kappa, derived from the Latin word dentis for tooth, which indicates the number of non-contiguous or not side-by-side donor sites by which a ligand attached to the metal. The angle between 2 bonds of a chelate means claw. Lepas dia gigit, dia cekau. Yeah. After it bites the metal, it becomes a claw attached. Yeah. So the word dentist for tooth and keel for claw comes into mind because they do look like a spit, yeah, spit claw. It calls chelate. When you have more than one donor atom, you call that a chelating ligand. A chelating ligand means a ligand which can claw. So bidentate ligand, tridentate, polydentate, they're all chelating ligands. Yeah. The angle is called the bite angle or chelating angle, which could be important for some properties or activities such as catalysis. Now, the field of coordination chemistry has been brought into attention by many avid and brilliant researchers well over 100 years today. This is almost 200 since Werner first published his paper in 1898. So let's count that. This is year 2020. Really, I'm not very good at mathematics. Let me see. Who can tell me 2020 minus 1898? Oh, I don't even have a calculator in my phone. Yeah, many, many hundred years ago. Over the century, more than 100 years ago, chemists have ventured into the wonderful world of transition metals and ligands, developing new frontiers of research and generating new knowledge, spilling into the neighboring fields of organometallic and bioinorganic chemistry. So I'm going to stop here and I'm going to let you simmer in that new knowledge. There is a lot of new things that you're learning today. So if you are having problem understanding, go through my notes, listen back to my lecture. I hope um, I really wish that I could be in front of you with my pen and my whiteboard drawing everything, which will make understanding a little bit easier for you. But never mind, we take the challenge of online learning full-heartedly. So I hope these new concepts that I'm introducing in this lecture, many, many new concepts, you can learn them very well, understand them, and we can have a discussion um, through our Telegram group. So this is 46 minutes, one of my longest lectures so far. I'm going to end it here and hope to see you again in my next lecture, which is lecture 11. So until then, Assalamualaikum.